Okay, let's unpack this. It's kind of mind-bending, isn't it? That the same core engine, the thing that powers like your phone understanding you,
Mm-hmm.
can also recognize cat photos
Mm.
or even do these incredibly detailed weather predictions. There's that Buy It All paper from 2022.
Right, on the spatiotemporal stuff, yeah.
Exactly. It just shows how this architecture handles all sorts of data, makes you wonder what's really going on under the hood.
It's the unity that's really remarkable. These things seem so different, language, images, weather, but they're all being tackled by the same fundamental tech, the transformer network.
Precisely. And that's what we're diving deep into today, this AI powerhouse, the transformer. Our mission really is to get past the buzzwords,
Mm.
and really grasp the core ideas, figure out why it's been such a game changer, and what makes it work across so many different data types.
Yeah, you've probably heard attention or transformer thrown around a lot.
Yeah.
But our goal isn't just definitions. We want to give you a real sort of intuitive feel for the key design choices.
Yeah.
Why is each piece there? What problem is it solving? We're focusing on the why behind it all.
And to help us navigate this, we're leaning on An Introduction to Transformers by Richard E. Turner. It's our main guide for this exploration. Think of us as kind of interpreting the key bits from that.
Yeah, Turner's paper does a great job. It's mathematically solid, but honestly surprisingly easy to follow in places.
It is.
Just what we need to get into the nuts and bolts.
So the plan then. First, we'll look at the basics, inputs and outputs, what goes in, what comes out.
Right.
Then we zoom in on the core transformer block. It's got these two main steps, right? Looking at relationships in the data, then refining the individual bits.
Exactly.
And of course, we have to talk about self-attention. That's the crucial bit, especially the multi-headed kind.
Mm-hmm. Can't skip that.
We'll also touch on why position encoding is vital, and then just briefly, how these core transformers get adapted for specific things like language or image tasks. Ready to peel back the layers.
Absolutely. Let's start right at the foundation. The input and output. What kind of data are we actually feeding into this thing?
Right. So transformers, according to Turner, they work with sets or sequences of tokens.
Okay.
Think of tokens as just the basic units. Could be words, could be parts of words, could be little patches of an image. And each token is represented as a list of numbers, a d-dimensional vector.
Got it. A vector for each piece of information.
Yeah. And Turner mentions he likes to think of these arranged in a D by N matrix. So D rows for the features and columns for the tokens in the sequence. He likes thinking of the sequence running horizontally.
And that matrix setup, which he shows in Figure 1, it's a really neat abstraction. It means the transformer can kind of handle all sorts of data the same way.
Exactly. Like take text, you break a sentence into word tokens, turn each word into a vector. Done.
Uh-huh.
Or images, like in that Dostoevsky paper on vision transformers.
Mm.
Or Figure 2, in Turner's paper, you chop the image into little squares, flatten each square into a vector.
Right. Image patches become tokens.
And that's the revolutionary part, isn't it? You're not stuck designing totally different networks for text versus images like you were with, say, CNNs and RNNs.
Yeah, it's much more unified. And Turner even hints you could mix data types, right? Feed in tokens representing different things all at once.
Seriously powerful idea.
Yeah.
Okay, so we put in this D by N matrix, X0, he calls it. What's the transformer actually do with it? What's the goal?
Well, the main goal, as Turner lays it out, is to take that input matrix X0 and process it through, let's say, M layers to produce another D by N matrix, XM.
Okay, same shape out as when in.
Exactly. But the key thing is that each column vector in that final matrix, each token's representation has been refined. It's soaked up information about its context within the whole sequence or set.
So we still have vectors for each original token, but now they're smarter. They know more about their surroundings. And these enhanced vectors, they're useful for downstream tasks.
Precisely. Turner mentions a few big ones, like autoregressive predicting the next word, like your phone's keyboard does. Or classifying a whole sequence sentiment analysis, maybe, or sequence-to-sequence tasks, like translation, even image-to-image stuff, lots of applications.
Okay, got the inputs, got the outputs, got the uses.
Yeah.
How do we get from X0 to XM? That's where the transformer block comes in, yeah.
Yes, that's the core building block. The transformation happens by applying this block over and over again. Turner writes it as XM equals transformer block of XM1. You just repeat that M times.
And inside each block, you said there are two main stages happening one after the other.
That's right. Stage 1 operates across the sequence, horizontally if you're thinking of Turner's D by N matrix.
Okay.
Basically, it refines each feature, each row, by looking at how all the tokens relate to each other. Think about word meaning depending on context, or how different parts of an image relate.
So understanding the context for each piece within the bigger picture.
Got it.
And stage 2.
Stage 2 then works across the features, vertically in the matrix. Here, the representation of each individual token gets refined. So after looking at relationships between tokens, you then enrich the description of each token.
Ah, okay.
Turner actually draws a parallel to things like graph neural networks or even ResNets, where you see similar patterns of processing across different data dimensions.
That makes sense. So this interplay information flows between tokens and also within each token's own representation layer by layer. Okay, let's dive into stage 1 then. Is self-attention across the sequence. This feels like where the real, magic happens.
It really is central. So the output of this stage, let's call it YM, is another D by N array. And the core idea is attention.
Right.
Specifically, the output vector at position n, YMN, is calculated as a weighted average of the input vectors at all positions in prime, so XM1 M prime.
Okay, averaging all the inputs to get each output,
Yeah.
but weighted.
Exactly. And the weights come from the attention matrix, AM. Equation 1 shows this. For each output position n, the weights AM and prime tell you how much input position in prime should contribute.
So for every output spot, we look at all the input spots and decide how important each one is for this specific output spot using these attention weights.
You got it. And Turner points out this attention matrix, AM, it's n by n, and it's typically normalized, so the weights for each output n add up to 1 across all the inputs in prime.
Makes sense, like probabilities.
Yeah. So intuitively, AN prime, n will be high if input n prime is really relevant for output n, and low if it's not. He gives an example of parts of an object in an image attending strongly to each other, and the whole thing can be written neatly as a matrix multiply. YM equals XM1 times AM. Figure 3 shows that matrix view.
Right, so the attention matrix is like a dynamic filter saying, pay attention to this part of the input when calculating that part of the output.
Yeah.
But where does AM come from? How does it know what's relevant?
Ugh, that's the self part. It's brilliant, really. The attention matrix isn't fixed. It's calculated from the input sequence itself.
Okay, how?
Well, a basic way, shown in equation 2, is just to compare the feature vectors. You take the dot product between the vector at position n and the vector at position n prime. That gives you a similarity score. Then you run those scores through a softmax function to turn them into probabilities. Those are your attention weights.
So things that are similar attend more to each other. That seems pretty intuitive for finding relationships within the data.
It is. But Turner notes a potential issue. This simple dot product kind of mixes up how similar things are with the actual content of the vectors.
Okay.
So an improvement shown in equation 3 is to first project the input vectors using a linear transformation, a matrix U, before you calculate the similarity.
Project them first. Why?
It helps decouple things. It lets the model learn what aspects of the vectors are important for deciding similarity separate from the raw content, like focusing on specific features when checking relatedness.
So the projection U lets us look at the tokens from a specific angle before comparing them. Okay. And then the paper talks about making it asymmetric, using different matrices, UKey for query and UK for key. What's the benefit there?
Right. Using separate query UQ and key UK transformations allows for non-symmetric relationships.
Non-symmetric.
Yeah, like Turner's example, caulking iron and tool. A caulking iron, the query, should strongly attend to tool, the key, because it is a tool.
Sure.
But tool, as the query, might attend less strongly back to caulking iron as the key, because tool is way broader. This asymmetry gives the model more flexibility to capture those kinds of nuances.
Got it. So it's like asking specific questions, queries about each token and checking them against certain properties, keys of all the other tokens. Much more sophisticated. Okay, now, multi-head self-attention, MHSA. Sounds like we're doing this attention thing multiple times in parallel.
Exactly right. Turner explains that to really boost the power of this stage, the transformer block uses H-parallel self-attention mechanisms. These are the H-heads. Each head gets its own set of query, UKey, and key, UKey matrices. That's equation 6. They all calculate their own attention weights and weighted averages in parallel.
So H different attention calculations happening at once.
Yep. And then the outputs from all H-heads are combined and projected back to the original dimension D using another set of matrices, the value matrices, VIM. Equation 4 and figure 4 show this.
And the V matrices, they're involved in the weighted average part.
Well, technically, the attention weights, calculated using UQ and UK, are applied to representations derived from a third set of transformations, the value matrices UK, applied to the original input. Then the results from all heads are concatenated and projected by VOEM. So each head learns different Q, K, and V transformations.
Okay, wow. So each head is learning potentially different query, key, and value transformations. Let's say each head learns to ask different questions, look for different keys, and extract different kinds of information values based on those relationships.
That's a great way to put it. Each head can specialize in capturing different types of relationships or similarities in the data. Maybe one head looks at syntactic relationships, another at semantic similarity, another at positional closeness,
So it's like having multiple experts examining the sequence simultaneously, each focusing on different patterns and then combining their findings. What's the main advantage?
Turner emphasizes it just massively increases the model's capacity to understand complex relationships. Things might be related in multiple ways. MHSA lets the model capture that diversity. He does mention the computational cost, though OHDN squared. That n squared part from the n by n attention matrix can be a problem for really long sequences.
Right. Comparing everything to everything else gets expensive. Okay,
Yeah.
so that's stage one. Multi-head self-attention figures out all these complex relationships across the sequence. What about stage two? You said it uses an MLP across features.
Yes. Stage 2 takes the output from the MHSA stage, YM, and processes each token's vector individually. It applies a multi-layer perceptron, or MLP, to each column vector, YMM.
An MLP.
Yeah.
Like a standard little feed-forward neural network.
Exactly. And crucially, as Turner points out, the same MLP, with the same weights, theta, is applied independently to every token location n.
The parameters are shared across all positions.
Right. So after we figured out how tokens relate to each other globally using MHSA, we then use the shared MLP to refine the features within each token based on that new contextual information.
So context first via attention, then individual refinement via the shared MLP, a two-step dance within each block.
Precisely. And you stack these blocks, but not just directly. As Turner explains, there are two other absolutely critical ingredients: residual connections and layer normalization.
Ah, yes, residual connections. That's where you add the input back to the output, right? Like XM1 plus the output of the layer. Why is that so important?
Yeah, that's the basic idea. Turner highlights a few big wins. First, it makes initialization easier. If the layer starts out doing nothing, residual part is 0. The input just passes through. Second, it encourages learning changes or deltas rather than entirely new representations from scratch. But maybe most importantly, it massively helps with training stability. It combats the vanishing or exploding gradient problem in deep networks.
Right, because the gradient's a shortcut path back through the network.
Exactly. And he notes these are used around both the MHSA stage and the MLP stage within the block. Figure 7 shows the structure. It seems simple, but it's fundamental for training the really deep transformers that learn complex patterns.
Makes total sense. Easier to learn small tweaks than whole new functions. Okay, and the other piece, layer normalization. What's its role?
Layer normalization, or token norm, as Turner prefers to call it, to avoid confusion with how it's sometimes used in CNNs,
Okay, token norm.
is another key stabilizer. It works independently on each token's feature vector. For each token, it subtracts the mean of its features and divides by the standard deviation.
Normalizing each token's vector on its own.
Yep. And then there are usually learnable scale, gamma, and shift beta parameters applied after. Turner explains this helps prevent the feature values from getting wildly large or small as they go through all the nonlinear transformations in the network.
Ah, keeps things from blowing up.
Basically, yeah. And like residual connections, it's applied before both the MHSA and the MLP stages, typically. Again, seems like a detail, but it's crucial for making these very deep networks trainable. You can see the structure in figures 5 and 6.
Okay, so residual connections help information flow and make learning easier, while token norm keeps the numbers in check. Sounds like you absolutely need both to build effective deep transformers.
Got it. Now, one more big piece we skipped: position encoding. Why do we need that?
Ah, yeah, critical point. The transformer architecture we've described so far, attention, MLPs, it treats the input like a set of tokens, not a
A
sequence.
set, meaning order doesn't matter.
Exactly. If you shuffled the input tokens, the MHSA and MLP operations would produce the same output vectors, just also shuffled. The relationships it finds are based on content, not position. But order does matter for loads of things, like language. dog bites man versus man bites dog.
Precisely. So we need a way to inject information about the position of each token into the model.
How do we do that?
The most common way is to add a position embedding vector to each token's initial embedding vector, x0n.
Adding another vector.
Yeah. This position embedding encodes the token's location in the sequence. It could be a fixed embedding, like the sine and cosine functions used in the original transformer paper.
Ah, the sinusoidal embeddings.
Right. Different frequencies encode different positions. Or, as seen in models like BERT or vision transformers, these position embeddings can be learned parameters, just like the word embeddings.
So the model learns the best way to represent position.
Exactly. Turner also gives a little intuition in a footnote, suggesting adding is related to concatenating position info and then using a linear layer. The point is, you somehow merge position information with the token's content information right at the start.
So we basically give each token a tag saying, I'm token number 1, I'm token number 2, etc., in vector form. That way, the attention mechanism can use both content and position when figuring out relationships.
That's the gist of it, yeah. And Turner briefly mentions other ideas too, like modifying the attention mechanism itself to account for relative distances, citing some recent work. But adding or learning position embeddings is very common.
Okay, great. So we've built the core transformer, input tokens, with position info added, go through multiple blocks, each block doing multi-head self-attention relationships, and then shared MLP processing, refinement, stabilized by residuals and layer norm. That's a lot. Now, how do we actually use this for specific jobs like language modeling or image classification?
Right. So the architecture we've built is like the transformer's main body. For a specific task, you usually add a task-specific head onto the end.
A head, like another layer or two.
Yeah, usually a relatively simple layer, like a linear layer or a softmax, that takes the final transformer output and makes the prediction you need. Sometimes you also tweak the body itself slightly for the task.
Okay, let's take autoregressive language modeling first. Predicting the next word. What's different there?
Turner points out two key things. First, and this is crucial, you need to make sure that when predicting word N, the model only looks at words 1 to N1. It can't cheat by looking ahead.
Right. That makes sense for generation. How's that done?
By using autoregressive masking in the self-attention calculation. Essentially, you modify the attention matrix so that any token N can only attend to tokens in prime, wherein prime is less than or equal to N. It forces causality.
Ah, you zero out the attention scores for future tokens.
Exactly. He notes this masking also makes training and inference efficient. You can process sequences cleverly, and it gives you that nice incremental property. Once you predict word N, its representation won't change when you predict word N plus 1.
Okay, masking enforces the past predicts future rule. What about the head for language modeling?
For that, you typically take the final output vector from the transformer corresponding to the last input token, say token N1 if you're predicting token N. This vector now summarizes the preceding sequence. You feed that vector into a final softmax layer. The softmax outputs probabilities over your entire vocabulary, say W words. The highest probability tells you the model's prediction for the next word. Equation 7 shows this, with weights glue for each word.
Got it. Masked attention in the body, softmax layer on the last token's output for the head. Makes sense. Okay, what about image classification? How does a transformer tell us if it's a cat or a dog in a picture?
Right. So as we discussed, you first turn the image into a sequence of patch tokens.
Yeah, the vision transformer approach.
Then, one way to classify is to take the final output vectors for all the patch tokens from the last transformer layer and somehow aggregate them. Maybe just average them together?
Okay, combine all the final patch representations.
Yeah, that gives you a single vector representing the whole image. You then feed that vector into a standard classification head, like a softmax layer, to get the image label probabilities.
Okay, aggregate the patch info, then classify. Simple enough.
But there's another approach Turner mentions, which often works a bit better. You add a special extra token to the beginning of the sequence of image patches, like a dedicated classification token.
A class token. Like the CLS token in BERT.
Exactly like that. This token goes through all the transformer layers along with the image patch tokens. Its job is basically to interact with all the patches via self-attention and build up a summary representation of the entire image. Then, for the classification head, you simply ignore the final output vectors for all the image patches and only use the final output vector of that special classification token. Feed that into the softmax.
That's clever. So instead of averaging patches, you have one token whose whole purpose is to learn the global summary needed for classification.
Precisely. It often learns a representation more tailored to the classification task.
Very neat. And yeah, Turner also quickly mentions more complex things like encoder-decoders for translation, masked autoencoders for pre-training.
Yeah.
It really shows how flexible these blocks are.
Absolutely. The core transformer block has become this incredibly versatile component used in so many state-of-the-art models across, well, almost everything now, it feels like.
Well, we have definitely covered a lot of ground today. We've really tried to unpack the transformer, haven't we? Looked at how it handles sequences with self-attention, how it refines features with MLPs, those crucial bits like residual connections and layer norm that make deep models work, plus position encoding, and how you adapt the core for different tasks like language or vision.
Yeah, and what's striking is how this, relatively coherent set of ideas leads to models that are just so incredibly powerful and adaptable. The transformer's knack for learning relationships in data, text, images, whatever, really has been a genuine revolution in AI.
And hopefully, by getting into these fundamentals, you, the listener, now have a stronger base for understanding all the new developments happening all the time. You've got a deeper insight into how these models actually learn and why they're so effective.
Which leads to a really interesting thought to maybe leave you with. How could these core principles, attention, feature transformation, be applied elsewhere? To totally different kinds of complex data, problems outside language and vision, what new ways could we tokenize information to unlock even more applications for this amazing architecture? Something to ponder, definitely.